All right, here's what we did. You guys took a still familiar? You got a ramp. You got a car. That's the company that makes physics equipment. They specialize in science equipment. And the car's going down the hill. And we've got a little doodad on here.
You have the drawing.
No, you don't have, I mean, the notes you take is just whatever. Remind me, you did not just diss my sketch. So car's going down. Okay? This is what we did. And as a result of this, we got a graph. Distance, time, and it was a curve equation. So, here we go. We're going to drive an equation with dt. Okay. And we're going to make an equation y equals mx plus b. It's going to be our base weapon, our base to actually derive all the equations. But there's a problem. That's for linear, so it doesn't work here. No good. It doesn't work here. So what do? We squared the x-axis, kind of different shape. So we straightened it. Okay? I saved us some time. I went ahead and told you. Okay? So that's good. That's valuable for us. But here's the question. What does the slope represent? What does the slope represent? You don't know. Okay? You don't know. All right? It's unknown what the slope is. This is not a standard type of thing. So here's what you're going to do. You're going to compare it. Here's what we did. We compared comparison. We're going to do a comparison between these two. That's what we just did. Because do we know what the slope of a BT graph represents? That's acceleration. That's not an issue. We know that. Okay? Some of you may not really understand acceleration yet. You've experienced it, but you may not really. But we know BT graph, the slope is acceleration. A DT graph, the slope is velocity. But a DT squared, what is that? Okay. So what we discovered from this is there's a relationship between a BT and a DT squared graph. And that relationship is, if BT is acceleration, then this must be 1/2 the acceleration. Okay, so now we know, and we know. We know these two things. They make sense to us. So let's derive an equation for both. For this one, y equals mx plus b is going to be what we use. And we're just going to substitute. On our y, we have a d. It's not. Okay? The slope is represented by 1/2 a. So I put 1/2 a. On the website, you're supposed to do ohms also, as your number. All right, x, what's on the x-axis? D squared, and what is crossing the y-axis at this point? I didn't say that right. Y-intercept is where it crosses that y-axis. Where does it cross the y-axis? Maybe 0, maybe it's not 0 for you guys. But actually, for most of you, probably wasn't. Depends on when you hit start.
Oh.
But I don't want a number. 0 is a number. I want a variable. What's the variable? D. It crossed the y-axis, and then the y-axis is D. D sub naught. This is D naught. If it's 0, we... All right, here we go. Now, let's go back. Let's kind of do a little side trip here. Okay? What's the side trip? It's like the bubble. Okay, we're thinking, You remember our original equation for velocities learned in middle school. Just as simple as that. And then I have complicated it a little bit, but B equals D over T. Can you solve for D there? Isolate the D. Multiply T both sides. Divide by V. So D equals
VT.
VT. If you rearrange that algebraically, this is the same thing. Now, if D equals VT, then D naught must equal V naught T. In other words, the velocity at D naught should be V naught velocity, initial velocity. At the beginning of the motion, in that position, should be the beginning of our velocity. Okay? At the final distance, which would be our total displacement, which should be our final velocity. So I'm going to, if this is D naught, this is V naught. I want to substitute this in. So I have a V now in my equation. Why am I doing this? I kind of know in hindsight what I want. So physicists kind of know what kind of tools they need. They can just make them out of thin air. Not really, but if you've got this, you got this, you can just kind of manipulate things to get what you want, as long as you don't break any math rules. Okay, we're not breaking any math rules. We're going to do simple substitution. Okay, we're going to substitute that in here. So that gives us D equals 1/2 A T squared plus D sub naught T. D naught. That's it. And the final, this is final D. So if I've traveled from D naught to D, then my total distance is D. A more appropriate way to describe that is displacement, my total change in position. So you can keep D if you want. I'm going to, for the rest of the semester, use X, and most textbooks that you look at, especially college textbooks, we're going to use X. So it's going to be X equals 1/2 AT squared plus V naught T. And then mathematicians have this thing about the simplest variables go first, and the more complex variables go next. You put them in order, and they go in alphabetical order. So technically it's A equals V naught T plus then the one that has the square on it, 1/2. And notice you're in alphabetical order, A, then the T squared. It doesn't go down. All right, so here's our first equation we drive. Now let's go over here and drive this one. Can we use y equals mx plus b here? Yeah, it's straight. Totally can. On the y is v. The slope represents a. X is t. And the y-intercept crosses at v sub naught. That's right. It crosses at v naught. Done. Let's just put them like in the math order. We would say v equals v naught, the simpler one first, plus at. That's simply how I write it. Here's our second derivation. And that one was easy.